Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series dedicated to you, the research and academic quantum communities. In just a minute, I'll be thrilled to roll out an episode 152, with the work that I'm personally very excited about, with Elisa Bäumer from IBM Quantum. A familiar face to many of you here, I'm sure, today in the audience. Now, before we get there, I'm so glad you joined us on time. We have a tradition here to give everyone just about a minute or two to tune into the live stream, and meanwhile to get active in the chat. You guys already know my favorite question, which is, where are you tuning in from today? You can reply to that in the comment chat box located somewhere on your YouTube screen, above, below, left or right, and let us know, because that is the same place where you can ask questions live of Elisa and myself during the seminar anytime, and I'll try to triage them and bring them up to Elisa so we can have an active, interactive, live discussion, which is why this is the live quantum seminar. And with that, I'd also like to bring your attention to two pieces. One, we have a new Quantum Crosstalk series where we sit down with influential members of the IBM Quantum team. So check that out on the YouTube channel to know what else is coming up. Click like and subscribe. And maybe see you at APS March meeting next week in person. So we will be off for the seminar. So folks, with that, this seminar takes place every Friday at noon Eastern time, except for March meeting. You can always go back and rewatch these episodes, but the only time to ask questions live is right now, 12 to 1. So with that, it's time we get started. I am your host, Zlatko Minev from IBM Quantum Research, and today I have the pleasure to introduce you to my friend and colleague, Elisa Bäumer, to tell you about her work that I'm very excited about. Hello, Elisa. How are you today?
Good, thanks.
And tell us, since you do globetrot quite a bit, where are you tuning in from today yourself?
I'm in Zurich, in Switzerland.
In Zurich, Switzerland. Well, I'm happy to tell you that here we have Kevin from sunny San Diego. We got folks from Dallas, Northwest New York City, Colorado, Tunisia, Yokohama, Ecuador. So thank you, folks, for making the many time zone differences. Elisa, before I let you take it over, allow me to share your bio with folks. Elisa is a research scientist at IBM Research Zurich. She received her PhD in quantum information theory from the ETH in 2022. And as you may know, Elisa is an avid outreach influencer, let's say, who does many activities such as lecturing and hands-on workshops for students, developers, and researchers. So with that, Elisa, the stage is yours.
Thanks a lot, Zlatko, and thanks everyone for tuning in for today's Qiskit seminar. So for those of you that follow the Qiskit seminars regularly, you might have seen me already last fall when we had this Qiskit seminar panel session where we highlighted recent work with 100 plus qubits. And well, there I only had summarized my work on one slide. So now I'm happy to dedicate today the full seminar just on that. As Zlatko mentioned, anytime you have some questions, please just put them in the chat and I'm very welcome to answer them as soon as I get them. So to give you an outline of today's presentation, I'm first going to introduce you to dynamic circuits and why they're useful. Then I'm going to show you how we can use them to create long-range entanglement by also walking you explicitly through an example of creating the GHZ state preparation. And then finally, I'm going to show you experimental results both for the GHZ state preparation and the CNOT gate teleportation. So let's start with dynamic circuits. What are dynamic circuits? Dynamic circuits are some quantum circuits that incorporate a couple of different features, which are mid-circuit measurements, which means that we can not only measure our qubits at the very end of the circuit, but at any time in between. Then classical calculations that are based on such measurement results. And finally, feed-forward operations, which means we can apply gates conditioned on the classical outputs within the coherence time of our qubits. Now, we can put all these things together and incorporate them in a bigger circuit, and then that's how a dynamic circuit could, for example, look like. And in fact, this circuit you will see later on in more detail. But now you may wonder, why is that beneficial? So first of all, maybe, why do we want mid-circuit measurements? And there's a very common example, which probably a lot of you have already used, maybe without knowing that it is like a dynamic circuit, which is the conditional reset. So if we have a state and we measure it, and then we apply a classically conditioned gate, a bit flip based on that, that means that if we measured the state 0, we don't do anything and we keep it in 0. While if we measure the state 1, we apply the bit flip. So in the end, the state will be for sure in state 0, and this is how conditional resets are actually implemented. So if you ever do a reset in your circuit, you will see that this is where we do mid-circuit measurements plus the feed-forward. Now you may also wonder, why do we want classical calculations when we're saying how good quantum computing is? So why classical calculations now? Aren't quantum computers much more powerful? Well, the answer is that quantum computers are indeed expected to give an advantage, but only for certain problems. So definitely not for all kinds of computations. So in general, if we, let's say, just want to add up 2 bits, then classical computations are much faster, have a much higher fidelity, and have no connectivity constraints. This is also the reason why currently there's a lot of research going on about hybrid classical quantum algorithms, like for example VQEs. The point about these hybrid classical quantum algorithms, so VQEs, is though that we have a quantum circuit, we measure all qubits at the end, and then we have our classical algorithm which updates the parameters that we then feed into the next quantum circuit, and so on. So we have a quantum circuit, a classical calculation, a quantum circuit, and so on, run all successively. But we don't have feed-forward operations. So now the question is, why do we want these feed-forward operations within the coherence time of our qubits, which makes it, of course, much harder to implement? A very famous application for that is the quantum error correction, where the goal is that we can check for errors and then directly correct them in real time before they can spread through the whole circuit. But then a different example, which is maybe a bit less known, where we can also use feed-forward operations, is that we can use classical calculations as an information transfer to spread correlations fast. And I will give you more details on that in a bit. Because this, in the end, then, is what allows us to create long-range entanglement in a shallow quantum circuit. But now you may wonder, why are mid-circuit measurements useful? Don't measurements make our state collapse? Well, let's consider the following example. It's just an example on 3 qubits, so maybe some of you can even do the calculations in their head now. Otherwise, just trust me that it's correct. So we assume we have 3 qubits, we have 2 Hadamard gates and then 2 CNOT gates, and we measure the middle qubit. Now the post-measurement state on the 2 other qubits can be 2 different states depending on whether we measured 0 or 1. If we measured 0 on the middle qubit, the post-measurement state on the other 2 qubits will be 0, 0 plus 1, 1. While if we measured 1 on the middle qubit, then the post-measurement state on the other 2 qubits will be 0, 1 plus 1, 0. So in either case, we will have a Bell state, which is great. And both are happening with equal probability, assuming that there are no errors. However, since we don't know which of the 2 Bell states we have, this is actually a mixed state, because if we want to do now further operations, we don't know which state we're in. But this is where conditional gate becomes very useful. If we now apply a conditional gate conditioned on the output of the qubit that we have measured, and we apply a conditioned X gate, then that means if in the case where we measured 0, we have the state 0, 0 plus 1, 1, and we don't do it because it's a conditioned gate. It only becomes active if we measure the state 1. Otherwise, we do nothing. Well, if we measure then the state 1, so we're in this Bell state, then we apply an X gate, so a bit flip, to the second qubit. So we will end up in 0, 0 plus 1, 1 as well, if we swap the second qubit here. So the final state will in any case be the Bell state 0, 0 plus 1, 1, and will be in this pure state, which we can use now for the rest of the circuit. So using dynamic circuits, we can create entanglement without a direct link in constant depth. And maybe for 3 qubits, this is not surprising. But the nice thing is that we can actually do that for any number of qubits, and we can still do it in constant depth. We will see more details on that later. Which is, of course, especially useful for quantum devices with limited connectivity, as it can help us to overcome that connectivity. But also, even for devices that have an all-to-all connectivity, it can still be very powerful, as we'll see in a bit. Now you may wonder, though, why do we need to apply this feed-forward directly? Can we not just remember what we have measured here, and then in the end, apply everything just with post-processing? Well, the problem is that the post-processing only works as long as we can simulate the different outcomes through the whole circuit. So if I know how my states develop afterwards, so for example, if I just prepare a state and I measure it, okay, then I can apply that bit flip in post-processing. Or if I just apply a few gates afterwards, then I can at least still see how the bit flip would affect my final state. However, we know that quantum computing in the end, the goal is to run circuits that we cannot simulate anymore. And for those circuits, we need to apply the feed-forward directly. We cannot apply it in post-processing. So I've shown you now an example with just 3 qubits, but now let's talk about long-range entanglement. Why do we care about long-range entanglement? Well, it's a task at the heart of every quantum algorithm. Because one reason is that if we want to apply long-range entangling gates, which are long-range entangling due to local connectivity, as we have, for example, in our devices. Say I want to connect 2 qubits that are far away, then this is a long-range entangling gate. And of course, at least on our devices, we have a lot of those. But then even if we had an all-to-all connectivity, we would require it. But okay, we actually mentioned here, assume we have 2 qubits that are a distance n away, then the depth we would need would scale with n. But now, okay, even if we have an all-to-all connectivity, if we want to prepare a long-range entangled state, so a state that has entanglement on n qubits, then it would at least scale with depth log n, which would be for the all-to-all connectivity and otherwise even longer. However, using dynamic circuits, we can create long-range entanglement in a constant depth quantum circuit. Now you may wonder, why does that work? Entanglement cannot spread faster than its information light count, right? And that is true, but the information transfer here is not applied with the quantum gates, but we're actually performing it by the classical calculation. To give you an example, and because we have quite some time now for this Qiskit seminar, I would like to walk you through the explicit example of the GHZ state preparation. So assume we want to prepare a GHZ state. The easiest way to do so, not the most efficient one, but just an easy way, is to apply a Hadamard gate on the first qubit and then CNOT gates all the way down. So this would require a depth of n, but even if we had an all-to-all connectivity, then the standard unitary approach, so if we just allowed to apply unitary gates and no dynamic circuit, we would require at least the depth of that scales with log n. However, if we have the measurement-based approach, so if we use dynamic circuits, then for any number of qubits n, we could implement it in constant depth. So the circuit that you see here on the right, the depth does not increase. It's always the same in number of steps for any number of qubits that we have here in between. And this is the example that I want to show you because I thought it might be useful for all of you to get a bit of an idea of how we can even see that these 2 circuits are the same, because I guess it's not obvious to most of you, while the circuit on the left corresponds to the circuit on the right. We also, of course, have to note, though, that while the circuit on the right has a much shorter depth, because it is constant, while on the left-hand side it scales with n, we do have more gates on the right-hand side, so we essentially trade the depth for the number of gates and number of measurements here. So let's walk through this example, but before we go through the example, let us actually, we're considering here 7 qubits on the left and 7 qubits on the right, so that we don't have all the dots in between, but can be generalized to any number of qubits. And before we derive this equivalence that I just showed, let's look at some other circuit equivalences that were going to be useful. So first of all, we can note that if we have 2 CNOT gates that are both conditioned on the same qubit, then they commute, which means I can just swap them. If we have 2 CNOT gates that have as target qubit the same qubit, it's the same and they commute as well, and we can also just swap them. However, if we have 2 CNOT gates where one has the qubit as control and the other one has the same qubit as target, they do not commute anymore, and we cannot simply swap them, but we can swap them if we add an additional gate, this additional pink gate here. And I'll refer to this circuit equivalence now as purple diamond, just so you notice it later when I derive the whole circuit. Then another important identity that we need, or not identity. Well, it's a consequence of the principle of deferred measurement, is that the measurement commutes with a conditioned gate, so on the qubit where it's conditioned, which means that we can move the measurement through the conditioning, measure the qubit first, and then apply a classically conditioned gate. This will give the exact same statistics as the left-hand side. And then another last thing that I want to show you is some kind of notation that is also used for tensor networks, for example. It's the so-called cup, which is just this thing. And that corresponds to a Bell state. So Bell state, we know it's symmetric, so we can either apply Hadamard on the second or the first qubit, and then a CNOT corresponding to that. So it's a state 0, 0, plus 1, 1. And the reason why this is nice to write it this way is that assume we have a circuit like that. Now we can move our gate along the cup to the qubit above. So we can have these two are exactly the same. They give the same statistics as well. It's the same circuit. And then something else, if we have this cup followed by a CNOT gate, then we can know that we can write it this way, and the two CNOT gates cancel. And this is just the same as having a plus and a 0, one qubit in plus state, one qubit in 0 state, which I refer to now as the blue triangle. And we will use it actually the opposite way. So if I have a plus and a 0, I will replace that by cup plus CNOT. You will see that in a bit. Okay, so let's get started. I want to start now with this version of writing the unitary way for the GHZ state, which is maybe not the most efficient one, but it's like one where we can easily then derive the other equation, the dynamic circuit version, and of course they're all equivalent as well. So the first thing we do is we move those darker purple CNOT gates to the very right side. So we move each of them through one of the brighter purple ones, which is where we need the purple diamond. So we need these extra, since they don't commute these gates, we get the extra pink ones. One here, one here, one here. For every gate we move through, we get this extra gate. Then, in the next step, we notice that these bright purple gates, now those CNOT gates, they're all conditioned on a qubit that is in the state 0. So we can just omit them. They don't have any effect at all, because if they're conditioned on a qubit in state 0, well, they won't do anything. Then in the next step, we note that every second qubit here, we only need it at the very end to be in the state 0 and then apply the CNOT gate. That means we can do kind of anything we want on that qubit before. And you will see in a bit why this is useful. We can, for example, prepare it in the state plus and measure it, reset it to state 0, and then we only need the 0 in the end anyway. So we can do that. And of course, we're doing this because the other thing that I showed you before was when we have plus and 0, we can nicely get these cups with the CNOT. So now we have the cup and the CNOT for each of the pairs that are plus and 0, as I showed you before, the blue triangle equation. And then, now comes maybe a trickier part. What we do now is we remember that two CNOTs, if they have as target qubit the same one, they commute. So I can commute those two, just swap them, and then move the pink one up on the cup so that it ends up here. And then I'm doing the same with those two. I swap them and move the pink one up. So it's here. And I do the same with this. I move the purple one here, and the pink one I move up all the way here. So we get this kind of ladder of CNOTs, but now we have here all these Bell pairs. Then, well, this is still not very shallow. So we want to move all the pink gates to the left. In this case, it's only 2. Of course, if we had it on n qubits, I guess you can imagine how it would look like. Just the same longer line, it would move even more. But now for every pink gate that we move to the left, we again have these two anti-commuting, not commuting CNOT gates. So we get this extra orange gate here, and we get it for this pink one that we moved there as well. So we have those 2 orange CNOT gates that we get in addition while we swap the order of them. Here was again the purple diamond. And now the principle that we haven't used yet, the principle of deferred measurement, or the consequence of it, is that we move these measurements through the controls to measure right here. and we move this measurement also through the controls, and that one as well. That means all these CNOT gates, the pink, all the purple and orange CNOT gates will turn into classically conditioned gates. We measure, and then based on the classical output, we apply these x's. If it's a 1, if it's a 0, we don't. But now you notice this still doesn't have constant depth. So there's now basically a final step that we need to do, which is we need to move the measurements we want to move all the measurements to measure all at the same time. And then we notice that now if we flip the bit and then afterwards measure, we can as well first measure and then flip the bit. And similar here, we can first measure and then flip the bit, the condition bit, the condition on the output before. So we move them through, and then we apply this x basically here, because if we just flip the bit if it was 1, and we don't flip it if it was 0, it's the same as just adding up the 2 bits. So we add up the first 2 bits and apply the conditioned gate, the conditioned x based on the addition of the 2 bits here. And down here, we actually then have the addition of all 3 bits and condition on that, apply the x. So in the end, here we apply just the first bit. Here we apply the sum of the first 2 bits. And here we apply the sum of the first 3 bits. So condition on them and x. And now we're basically done. We just, again, put back, do the opposite way, and our ball states make them look like an actual quantum circuit. So transform them back to having Hadamard and CNOT gates. And now we're at the form that I showed you before, this dynamic circuit. So sorry if this was very technical. I just thought for some of you it might be of interest to see how to get from one side to the other. So then let's get to our experiment that we were running. So we wanted to compare how the unitary circuit compares to the dynamic circuit. And to keep it easy with the connectivity, we consider just a 1D line, so a 1D chain where you have nearest neighbor interactions with n qubits. For the unitary circuit, it's then better to start in the middle, because then the depth is only n over 2 instead of n if we start on one end. And then the dynamic circuit is the one that I just showed you before. Now the circuit depth for the GHZ state preparation, if we consider the unitary circuit, scales with n. This is like n over 2 in this case. While for the dynamic circuit, as I mentioned now a couple of times, it's constant. So no matter how many qubits we have, it will always be the same depth. We'll always have a Hadamard gate, then 2 layers of CNOT gates, the measurement and feed forward, and another layer of CNOT gates. This post-processing, as I mentioned before, we can only apply if the final state is not used. So if it's just about preparing a GHZ state, then sure, we can just apply the conditional operations in post-processing. But of course, if we would actually use the GHZ state and feed it into another algorithm, then if we cannot simulate it anymore, we couldn't do the post-processing, but would need to apply the dynamic circuit. But in our experiments, we just compared the post-processing to see how the fidelity drops if we do the feed-forward operations. So how much error comes from the feed-forward operations versus how much comes just from the rest of the circuit. Now you see here in yellow these slightly yellow shaded areas. And this is where we wanted to show where we have idling errors. Idling errors means errors that come from the qubit being in a state that is not 0, because if it's in 0, doesn't have large errors. But if it's non-zero, and here, for example, especially also entangled, then there's quite some errors on these qubits while they're waiting. So while they're idling and waiting for other operations to be performed. And here we can see that the yellow shaded area actually scales quadratically, because we have the number of qubits that scales with n. So we go from 1 to n qubits basically, and the depth also scales with n. While here we have just on n qubits a constant time, which we called mu, where mu is just measurement plus feed forward. We call that mu times half of the qubits n, so n over 2. So let's have a look at the error budget to see what we would expect, what kind of results to see. So for the unitary, I just said the idling time scales with n squared. So n squared over 4, because we have n over 2 depth, and from 1 to n qubits, basically. So this is quadratically, but with n squared over 4. While for the dynamic circuit, we have this n half qubits that weight the mu. So +1 in the beginning in terms of CNOT gate time. And then for the post-processing, we don't have to take an account for the feed-forward time, so it's constant. Then the number of CNOT gates that we have is much more for the dynamic circuit, though. So we have 1.5 times as much, basically, as the unitary circuit, where we only have n-1 CNOT gates. Plus, we have more mid-circuit measurements for the dynamic circuit. Now, since we know that the error from the idling time is in general much smaller than the error that comes from the CNOT gates and the mid-circuit measurements, we expect that for small n, the unitary method should be beneficial, because these errors are just much bigger than the error that we get here. However, since this scales quadratically, while these errors only scale linearly, we expect that at some point there's a crossover where then the dynamic circuits become more beneficial. So for large n, we expect that the dynamic circuits are advantageous over the unitary circuits. So let's look at the experimental results. First of all, maybe because I plotted here the fidelity, and it's important that if you want to determine the fidelity of a quantum state, so if you want to certify that, you cannot just measure in the Z basis and just say, okay, I'll take the probability to measure all zeros and plus the probability to measure all ones. But it's important for the GHZ state because we consider entangled states. We also care about the phase. And then the way you can certify the fidelity is to sample from the 2 to the n different stabilizers that we have. And that's what we did. And you can see here the unitary circuit, so the one in bright blue, turquoise. There we could observe genuine multipartite entanglement, which means a fidelity larger than 0.5 on up to 7 qubits before we apply dynamical decoupling. And we can see that it actually rapidly decays, which is mostly due to the ZZ crosstalk. But then once we apply the dynamical decoupling here on the right side, we can observe this genuine multipartite entanglement on up to 17 qubits. Yeah. For those of you who don't know about dynamical decoupling, just to give you an idea, the easiest pulse, not the one that we applied, but the easiest pulse would just be to wait and apply an X and wait and apply an X. So the idea in general is to apply pulses that cancel each other theoretically out the qubit, like just applying 2 bit flips. So we wait, apply a bit flip, wait, apply a bit flip. But then in between, if you have some coherent error, like some rotation, then the idea is that you have some rotation in one direction before, then you flip it and you have some rotation in the other direction afterwards, and that thereby these coherent errors cancel, and specifically also the ZZ crosstalk, for which you then also use more advanced sequences. Now, if we compare dynamic circuits, we can see that they perform quite poorly compared to the unitary circuit, unlike what we would expect according to the error budget. But there's basically 2 reasons for that. The first one is that in the end, the feed-forward time that we needed, it was not constant, but actually scaled exponentially with the system size, which was due to an implementation of the so-called switch that we used. So to apply this feed-forward, we have a switch which checks what the measurement output was. Like, was the, let's say we measured 1, 0, 1 on our 3 mid-circuit measurements, then ideally it would just say, oh, it's 1, 0, 1, so we apply X on that gate and on that qubit and on that qubit. However, the older way in how it was implemented was that it would check, oh, is the bit string 0, 0, 0? No. Is it 0, 0, 1? No. So it would go through all the bit strings until it finds the one that we have. And that means that on average, it goes through half of the bit strings, which is an exponentially increasing number. That's why when we ran those experiments, we had an exponential overhead in the feed-forward time, which is very small, but since it's then exponential, you could observe it. By now, we do have the capability of the so-called block engine, which means that it actually works in constant time. So it really just checks, what is the bit string? Oh, it's 101. Okay, then we do that. So it directly goes to apply the correct feed-forward operation. So we're planning to repeat the experiments very soon, hopefully seeing better results for the dynamic circuits. But then there's also a second thing, which also decreased the fidelity of dynamic circuits, which is the fact that we cannot apply pulses during the feed forward, which means that this dynamical decoupling, which greatly reduces our errors, as we can see from the unitary results, cannot be applied during the feed-forward time, which is one of the majority, like which makes a big portion of the idling time of the dynamic circuits implementation. So combining these two is why we see these rather bad fidelities, but hopefully very soon we'll gonna see better results there. However, we also should note that we look at the post-processing results, which basically indicate how the dynamic circuit results would perform if we had an improved classical processing. And indeed, they're substantially better than the dynamic circuits, but still they're not outperforming the unitary. They might do that we really expect them, looking at the theory, that they will do so for larger n. So we still expect that there is a crossover for large n, but of course that requires that the hardware improves further, and that we can also, for example, apply more error mitigation techniques like probabilistic error cancellation towards our mid-circuit measurements, and then eventually see a crossover. But then we also ran a different experiment, which is gate teleportation of the CNOT gate. And so let me show you the circuits there. And the idea is, let's say we want to apply CNOT. Yeah.
Maybe before you change sections here, quick question to clarify. And first of all, thank you guys for posting all the questions. We've been pretty active in the chat, so if you're only watching the video, check out the chat. We answered a bunch of questions in there. But just from Damien Moller, so if I understand correctly, due to scaling of the feed-forward time, the scaling of the feed-forward time was a technical problem, but that shouldn't be a problem anymore. They just wanted to understand that.
Yes, exactly. One still needs to, when using the Qiskit, I think you need to specify that you want to use the block engine, but actually not 100% sure if it's already by default implemented or not. But you definitely, if you use this block engine, you can do it now in constant time, which is great, which should give us a great improvement. Yeah.
Great. And do you want to tell us, are there any other limitations one should be aware with the block engine for this kind of experiment, or is that?
Yeah, there is another limitation on the block engine, which is the number of cases. I think it takes only 2 to the 11 cases. So then if you want to have more than 11 mid-circuit measurements, which would bring us to like 23 qubits, I guess, GSC said on 23 qubits, you would need to have multiple block engine switches, for example, or have nested if-else statements. But so at some point you're limited with that. But of course, people are working on further improving that. So we expect a lot more improvements over the next year, like also being able to apply pulses during the feed-forward time, but then also like in the classical calculation part, that if there's a different implementation that we can use rather than just the switch, there should be ways to circumvent the number of cases as a limiting factor.
Great. Maybe another question here from Kasim, I think. I think that's Kasim. Yes. Is there a version of the code for this work available somewhere?
I have to admit, I'm not sure about which tutorials have been made publicly available and which have not. But I guess we can double check that and maybe put the answer in the chat later. But the idea is to share all the code eventually. I think right now it's also a bit problematic, since I mentioned like the block engine, which is now newly available, which we haven't used. So it would maybe not make too much sense to put the old code. Plus now there's Qiskit 1.0. So there's a lot of announcements, I guess, which make it maybe harder to share old code. But for sure, at some point there will be code available. Yes.
Great. And a question from Kevin. Thanks, guys, for pouring these in. Oh gosh, there are even more pouring in. We've really stimulated the crowd here.
Okay, cool. Let's do that.
What is the theoretical maximum of incorporating real-time classical communication into quantum circuits? It's a hard question here. I think it's related to the bounds and limits on what you can and cannot achieve. And Kevin, feel free to clarify what you mean by that exactly, because I think that can be interpreted many ways.
Yeah, I guess given like the switch, as I said, there's like a maximum of 2 to the 11 cases, but then also there's the possibility to actually add bits rather than like for other applications, for example, the one that you will see next, you could just add up bits, and then in the end we have only a few cases. So I guess then you're maybe at some point limited by how many classical operations you can do within the coherence time of your qubits. But since classical operations, like adding 2 bits up, is very, very fast, I don't think we're going to hit that limit very soon. But yeah, I don't know what exactly the question was referring to, though.
Okay, great. Okay, well, this is an interesting question. Feel free to push back on it or reinterpret it. But let's see. Well, let's see how the interpretation is from Akshit Johri. Could you please explain again why the dynamic circuits perform poorly?
Yeah, so as I like why in our experiment they perform poorly is both because of the exponentially increasing feed-forward time that we had, which is the thing that by now should not be a problem anymore with the block engine. And then the other problem especially why we don't see a benefit from, or hardly see a benefit from using dynamical decoupling and not using it, is because we right now cannot apply pulses in the feed-forward time. So applying the dynamical decoupling is not straightforward. There are some schemes to circumvent that, to kind of trick it, but it's still not as good as if we could actually apply dynamical decoupling during the feed-forward time. But that's also a capability that we're hopefully going to have soon. So there's, yeah. And then maybe the third thing is that, well, we have a lot of mid-circuit measurements, and mid-circuit measurements, or in general, measurements have errors, but for final measurements, it's much more straightforward how to mitigate them, because we can just do like the M3, for example, with Qiskit, by now almost automatically applied, I think, very straightforward. But then for mid-circuit measurements, it's much more complicated how to mitigate mid-circuit measurement errors, because they influence then also the feed-forward operations. So there has been work on that, like using probabilistic error cancellation for that, and work from Pretty, for example, that I can highly recommend. But it's not, we haven't applied it here yet, because I think still need to make sure we can scale it appropriately.
Okay, and oh wow, okay, questions are pouring in. There's even more. I might have to cut off the discussion here and leave some for the end. But yeah, let's come back to some of these questions at the end, guys. Thank you, Manos and Damien. Just in terms of time control, I'll bring those questions back up at the end of your slides, Elisa. So
okay, yeah, I think I have another 10 minutes, maybe 10 to 12 minutes, I guess, and then after that, happy to answer all the questions till the full hour.
Right, so stay tuned, folks. We'll come back to your questions and keep posting them in the chat.
So let's have a look at the second experiment, the CNOT gate teleportation. The idea here is that we have n qubits, and I want to apply a CNOT gate between, let's say we have a line, just again to simplify it, let's assume we have a 1D line with nearest neighbor connections only, and I want to apply a CNOT gate from the first to the last qubit. So I have like a distance n, as I would call it now. Now, the way I would do it on a unitary circuit is I would need to swap my qubits all the way to the middle, apply the CNOT gate, and swap them back. And now here the swaps are only 2 qubits because I'm swapping with a 0, right? I now for now imagine those in the middle are empty qubits in the state 0. With a dynamic circuit, however, I can do it very similar to before, to the GHZ state preparation. So also the derivation would be very similar. I'm not going to go into that now. But again, I have like some Hadamard gates and then 2 layers of CNOT gates. And then I measure all the qubits in the middle in alternating bases. So X bases, D bases, X bases, and so on. And I apply feed-forward operations based on those mid-circuit measurements. Now, you may notice that actually the pink gates, CNOT gates here at the top, you could cancel them. They would cancel. Theoretically, you could get rid of all of them and not implement them. But then the depth would still be the same, because at the bottom you cannot cancel them. And what we noticed is that if we do that, we actually get worse results. Because if we apply both, that means we swap the qubit, because the other qubit is 0. So we do a full swap, which means these qubits here in the middle are in state 0. And that means we have no idling error. If we don't apply these gates, then we have entangled qubits everywhere here, and we get a much bigger idling error, which again scales quadratically then. So we figured out it's better to apply these gates, just for those few who noticed. Which then means we don't have an idling error, which is nice. On the dynamic circuit, we now also have only constant idling error because we only have it during the measurement and feed-forward time, and, well, 2 CNOT gates here, but only on 2 qubits. Not before it was on n qubits. That's why it's scaled with n. Now it's only on 2 qubits, so it's constant. Now the circuit depth, if we check this long-range CNOT gate on n qubits, we see that for the unitary decomposition, it scales with n, with a number of qubits, while for dynamic circuits, it's again constant. No matter how many qubits we are, always the same depth. And of course, again, we could apply post-processing instead of the feed-forward here for the dynamic circuit, but only if the post-measurement state is not used or if everything can be simulated very easily. But so in general, it doesn't make sense to use post-processing if we want to do that in a more complicated algorithm. So let's look again at the error budget. I said the idling time error for the unitary in this implementation. Now we compared a lot of different ways to implement it, like with less gates and more idling time errors and so on. There are a few different ones, but this one turned out to be the best one. Then we have for the unitary, we have for the dynamic circuit, we have the 2 mu plus 2, so also constant idling time error at least. And then the number of CNOT gates here, it's not like in the GHZ state, but actually kind of the opposite. We have less gates for the dynamic circuit, but we have 4 n plus 1 CNOT gates for the unitary circuit. But we do have n additional measurements that we need in the dynamic circuit. Now, we expect that for large n, given this error budget, which kind of takes care of the biggest errors, those that we can quantify and where we think they have the biggest impact, we expect that dynamic circuits should be advantageous over unitary circuits if the additional n mid-circuit measurements here introduce less error than the 3 n extra CNOT gates that we get in the unitary circuit. One thing to note, though, is that what we're considering here now is just the gate fidelity on the 2 qubits. So we just check for the gate error that we have on those 2 outside qubits. But let's say we want to implement this CNOT gate as part of a bigger algorithm. Then there would maybe be a lot of other qubits that are actually waiting for this operation to be performed, which would also have a much bigger error if we had the unitary case and a deeper circuit. And so in the end, we kind of expect that the constant depth dynamic circuit is even more advantageous than what we see from the gate fidelity, because the gate fidelity is really just on those 2 qubits. But okay. Then we run the experiment and we choose one D chain. So just as you can see here, this red line going through our 127 qubit device on the Sherbrooke. And here we can see the results. Now, first of all, this time it was not state certification, but gate certification that we had to do. However, we can use the so-called Choi-Jamelkowski isomorphism, which simplifies a bit the way you can determine the gate fidelity, because it allows to apply Monte Carlo state certification on the Choi states of our gate. So if you want more details on that, I would recommend to read the paper. I'm not gonna derive that now. But in the end, it was quite efficient to determine it. So you don't need to do measure in too many different bases. So for what we can see here in the results is that for n smaller than approximately 10 qubits, the unitary implementation yields the best fidelities, which we would expect because for the dynamic circuit, we still have this offset of the feed-forward time, which is constant, but then it has a bigger effect for a smaller number of qubits, while the other errors scale with n. But then as we increase the number of qubits n, we can see that the unitary, the bright blue one, converges much faster to the fidelity of a random gate, which is 0.25, than the dynamic circuit implementation, which converges to a value that is slightly below 0.4. Now we also plotted here the post-processing, just to see how good we could get if we didn't have the feed-forward, basically. We just applied it in post-processing, so to get an idea of how much better we can get if we improve the feed-forward. And while we see it gives better results, but yeah, the difference is not as big as maybe before for the GHZ state preparation. And again, be reminded, post-processing, we can do it here now where we just prepared this, just applied this one gate and checked the fidelity. But if we would incorporate it in a bigger algorithm, that would not be an option. But what we overall see is that CNOT gates over large distances are more efficiently executed with dynamic circuits than with unitary circuits. Now, as an outlook, and maybe you have noticed that when I draw the circuit, I assume that I have 2 qubits that are far away, and that in between all the qubits are clean ancilla qubits. So they're all in the state 0, which of course wouldn't work if I would use every qubit in the device as like a system qubit, so for the calculations for the algorithm. But what we can do instead is we can try to connect all system qubits with each other. So divide our chip into system qubits and ancilla qubits, and then connect them in a way, or like map it in a way that we have the system qubits that are all connected with each other system qubit via a so-called bus of ancilla qubits that we basically sacrifice to get a better connectivity on the system qubits. And so the ancilla qubits are then just used for measurement and feed forward, and are then always reset. So a potential division would look like this, where we can see in pink and in orange the system qubits, and then in bright blue, the turquoise, and dark blue, the ancilla qubits. And now the reason why some of them are orange is because those, for example, could easily also be sacrificed as even more ancilla qubits. Then we have less system qubits, but we can perform more gates in parallel. So that would be, then we could do more gates in parallel than we could with the current division, but would sacrifice more qubits. But I mean, at the moment we have quite big chips, so that might still be worth it. But yeah, so the idea is that teleporting gates could provide a workaround for an effective all-to-all connectivity. But of course, we need to also consider that our fidelities were still not that high. So it's not something one could directly do and just get an all-to-all connectivity immediately. Now, a last thing that we considered was combining multiple CNOT gates and then optimizing when you have multi-qubit gates, optimizing the implementation of basically multiple teleported CNOT gates. So as an example, we were looking into the CZZ or Toffoli gate. And then we actually noticed that an ancilla qubit allowed for much more efficient implementation in that case over the long-range ones. So usually the CZZ gate, or if we just add local rotations before and after, that would be a Toffoli gate. And so the decomposition usually is into 6 CNOT gates, but then CNOT gates between each pair of qubits. And we thought about implementing it this way, where we have an additional ancilla qubit, and then we have a few more CNOT gates. But that turned out to be much better if we apply a long-range CZZ, where we say that this qubit is now kind of in the middle of the 3 qubits that we want to connect to. Like you could nicely think of that on the map, on the chip. And then what's nice here is that if I wanted to directly implement this, then yes, I could just take each of the CNOT gates as a long-range CNOT gate and do a teleportation, but then I would require, in this case, 6 times the measurement and feed-forward time. And measurement and feed-forward takes quite a while, so if we have 6 of those, that introduces quite some error. But if we now combine it, we can move some things together, do some classical calculations together, and then in the end, we can do it with only 2 steps, like the dark green we can all do at once and the bright green we can all do at once. So we can actually optimize in that sense. I think there's a lot of room for improvement to general bigger gates or multi-qubit gates to improve those further as well, or general algorithms with multiple CNOT gates. There, I think one wouldn't need to do every CNOT gate teleportation one by one, but combine things smartly. But yeah, so with this, I'm at the summary and outlook. I hope I managed to convince you that dynamic circuits are a promising feature to help overcome our current limitations of real hardware, as they could drastically improve the circuit depth. We also expect that their effect will become much more significant as we scale up the number of qubits, as I explained. And well, we can already now see the benefit of dynamic circuits in some applications, but I think there's still many, many more to explore. So I'm looking forward to further applications. And with that, I would like to thank you for your attention, and I'm happy now to answer even more questions.
You didn't hear anything I said, did you?
What did you say?
I was muted, I think. I said.
Yeah.
I was saying congratulations, Elisa, on a great talk and a great collaboration. This was really fun work to do together. A lot of thank you, Diego, for the applause and the claps. I know we have a lot of questions to go back to, folks. Please repost your questions. So to make it easier to me to find, and also post any new questions you have for Elisa here as we come to our last few minutes. One of the questions that came up earlier was, let's see if I can find it. So one of them was about error mitigation techniques for mid-circuit measurements from Damien. And sort of how they relate to the mitigation techniques in normal circuits. Are there any equivalences between mitigation techniques for normal circuits like PEC and mitigation techniques for dynamic circuits, such as the ones you have?
Yes. So there's some mitigation techniques that you can, for example, not straightforwardly use, like the measurement error mitigation, because if your further operations also depend on that measurement, on the measurement outcomes, then if you correct for the measurement outcomes, you would also need to correct for the feed-forward operations, and that, of course, makes it much more complicated. So you cannot directly use the normal, for example, the M3 with Qiskit, the normal measurement error mitigation, but then you could instead, for example, use basically PEC, like probabilistic error cancellation, and characterize your measurement and the map there, the errors with that, and try to apply that to your mid-circuit measurements. So this is a way that can theoretically work, and there's some work that was published, I guess, or at least on the archive a few months ago that you can find. I don't know, maybe Slatko, you can put the link in the chat if you have it.
Yeah, I can try to put it. It's really Gupta.
Yeah, it's one example where, and then, I mean, things like error suppression techniques, of course, were still the same. Well, we have dynamical decoupling schemes that are usually then slightly adapted, because during the mid-circuit measurements, there's different interaction on your other qubits as well, or can potentially be, but you can still apply dynamical decoupling sequences. And yeah.
Thank you, Elisa. We have a lot of questions, so I'll press to the next one. Manos Giortamis. The performance impact of dynamic circuits, mid-circuit measurements, also affects other techniques such as quasi-probability distributions, such as its use in wire or gate cutting algorithms. Do we have any estimate on how or when the performance of these mid-circuit measurements, which was so essential to our work here, will improve?
I guess the question is when it will improve, because I guess it's constantly improving. The question is just, it's not, I don't expect it to be a step function, but more like a smooth improvement curve, basically. So I think it's basically almost every day, it's really constantly improving. And if you look at our roadmap, you can see that we expect to have error correction in a few years. And for that, we need dynamic circuits. So, I guess that gives you an idea how much we expect dynamic circuits to improve over the next years as well. I don't have exact numbers that I could tell you, how many percent I would expect it to improve in the next year. But because also it's an interplay of both the experimental improvements, but then also the theoretical ones, like mitigation techniques. I hope that answered the question.
Okay, thank you. And maybe a question here from, thank you guys for pouring these in. I'm going to get through this slowly. What about transpilation from Akshit Jori? Was transpilation considered for optimization here? At what level can that, or does that help us?
So for unitary circuits, we transpiled everything, but then we also, as I said, we compared a lot of different implementations ourselves. So for example, those CNOT gates that would cancel, we figured out it's actually better to not cancel them. And so in the end, we transpiled it ourselves. But I think it's also easy enough circuits that you can determine by yourself how the different options of transpiled circuits. And then for dynamic circuits, there's no transpilation yet that would directly turn your unitary circuit into a dynamic circuit. So that would, of course, be great. And I definitely think it's something that we should investigate. But it's not there yet. So the dynamic circuit, you need to derive yourself, kind of.
From Himanshu Sahu, I found dynamic circuits really powerful. How to compare their performance with circuit cutting approaches, where you could effectively teleport a gate using a quasi-probability distribution without actually implementing any.
Yeah, so of course, circuit cutting will have better fidelities, because for circuit cutting, you don't need to prepare those Ball states, but you, I guess if you're familiar with circuit cutting, the person asking, then you know that for circuit cutting, you don't prepare that state in the end, but you just sample, like you theoretically build many different circuits so that on average, you get the right output. But then the problem is that you have a sampling overhead. So your fidelity is going to be better, but you will need to sample more circuits. So it will take longer. And then if you have that scales exponentially as well, the sampling overhead. So it's a bit of, I guess one could also try to combine both in general. That might be even the best option, to depending on the connectivity and the algorithm, to combine it. Yeah, but the fidelity should be better with circuit cutting.
Yeah, and maybe I can add my own opinion here.
Oh, yeah.
Well, because circuit cutting is another kind of quasi-probability technique, and this was when I started the probabilistic error cancellation experiment. This was one of the biggest challenges: is how do you actually scale it really far? And we came up with a model to do that for the mitigation piece. In circuit cutting, you have at least two challenges. One is readout errors can very much affect your distribution, so you have to be careful with that. And when you combine the counts from the different partitions of the circuit, and the other piece is the scaling. The scaling is very, very steep, exponential. So I'm pretty sure you can do things with dynamic circuits here that are far out of reach of those that you can do with circuit cutting when things get more complicated. So I imagine that long term you'd want to really be able to figure out dynamic circuits, but the entry point is harder.
Yeah, I fully agree. That was a good explanation. Yes.
Okay. From Akshat, why use a 1D chain? Could there be better circuit shapes that could improve the results?
Yes. So if I, for example, look here again at the connectivity map of the device that we're using, Sherbrooke, then of course for example, the GHZ state preparation, it would make more sense, or also the teleportation. If I want to teleport from here to here, I now went all the way on this one line rather than going the most direct way. The idea was more that we wanted to compare, if I give you a line as if I would now run this experiment or try to get teleportation working on a qubit on a chip with 1,000 qubits, then maybe the longest distance would actually be 100 qubits, like not considering a 1D line, but even considering the shortest distance, like going from one end to the other. So we really just wanted to see how does it scale up, and to scale it up, we wanted to see if we restrict it to be on 1D line. Like there's not really too much point, I guess, in seeing, okay, what's the performance from this qubit to this compared to from that to that. So even if both of them have like the distance of 3 or something. So we really just wanted to see how does it scale even further than what we would maybe realistically have as a longest distance. But yeah, of course, if we would consider all the connections here, we just wouldn't have a distance of 100 qubits ever. But the longest would be, I don't know, 20 or something.
Okay, thank you, Elisa. Question from Muzamelia here. A question earlier, are the cups you showed, the very nice visual graphics, are they the same calculations coming from Bob Koki, who we've had on the seminar, by the way?
Yeah, so there's a lot of parallels. So I'm really just using kind of a, I guess, simplified word. Like I'm just thinking of quantum circuits, and yeah, but you're right. Bob Koki has this like ZX calculus, where he defines these spiders and X and Z bases and how to then and that in the end you can also see how you can simplify circuits and move gates around. And so basically that work is a generalization of what I'm doing. I'm really just using very simple inequalities that I guess we would also be able, I'm pretty sure we would be able to derive them when using the spiders. And he basically, this is the like full generalized description of more generally how to move things around and so on. Yeah, this is just some examples that are particularly useful here, but it's the same. Yeah.
Thank you, Elisa. A question from C.A. Felekis and from Manos, basically the same question. With the new Horne processors, where you have like 3 separate chips by 133 qubits each, which are not physically necessarily connected at the same level, or they are, basically whatever the setup is with the classical real-time communication, can this technique be used across multiple quantum processors? Maybe to simplify the question, can this technique be used across multiple quantum processors?
Yes, it can. I mean, it would require now, if we're not using circuit cutting, but actually only teleportation, then we would require a quantum link between the chips as well. So we would require both one quantum link at least and classical communication. But then also one could, for example, cut at one point, use circuit cutting, and then use that for one cut in between and do everything else with quantum gates. But yeah, it could be used there as well.
Excellent. And a question from, sorry, a new question just jumped in, but maybe let's do Kasim's question first, since it came first. Can you explain a little more about how your implementation of the CCZ, the control CZ gate, is better? I suppose better than the unitary version. Kasim, please.
So we actually have not run an experiment here. It was really more to show the idea that if we here have this extra ancilla qubit, we can, using that kind of setup, we can combine multiple feed-forward operations rather than having. So if I would just take this CCZ decomposition and assume that I have a lot of qubits between all my 3 qubits, that there's a lot of qubits in between, so I have long-range topology, then if I would now apply the CNOT gate teleportation to each of them, then I would have 6 times the measure and feed-forward time, which takes a while. Well, we then just showed as an example for the CCZ or topology gate that you can combine them. So you can combine here some calculations, and if you can combine them, you only need to wait twice this measurement plus feed-forward time and not 6 times. So this is just an implementation, but we haven't experimentally implemented it yet. It was more a theoretical idea that we wanted to show that it can be, that there's still a lot of room for optimizing various kinds of algorithms given these teleportation schemes that go beyond just CNOT gate teleportation.
Great. And question from Damian Muller. The way I understand it, after a mid-circuit measurement, the qubit becomes available. Would it be possible to reuse the ancillas without resets, with resets, and try to parallelize the circuits even more?
That would be the idea already, I guess, or maybe I misunderstood the question. So the idea is that every time I do a CNOT gate teleportation, all these qubits are directly reset. So if I look at the, you don't see it here, but basically while I'm doing the feed forward here, I can as well, in the meantime, also reset all the qubits. So the idea is that in the end, maybe I should have clarified this here in the plot, all these qubits would again be in 0. So then, yes, you can still reuse them later, but you cannot use them at the same time. Or at least not straightforwardly. It's not not that clear. Yeah.
Excellent. Great. I think that's it for the questions, folks. Thank you, Elisa, for allowing us plenty of time for questions. There was quite a few.
Well, I'm very happy that there were so many questions. So it seems like a lot of people actually were following, or at least some.
Yeah. We've had a pretty nice large crowd today on episode 152. Never thought it would get to that many. It just keeps rolling and steamrolling. So thank you, Elisa, for the wonderful work. Congratulations again to you and the team and your colleagues.
Including you, yes. There was great collaboration. Thank you.
And thank you, Kevin, Simanos, everyone who asked all the great questions today. This will stay recorded, so folks, you can go back and rewatch it. Come see Elisa's talk on this paper at March meeting next week. I'll be there as well. I'm giving a talk as well. So come see me and say hi. And with that, I'd like to thank you, Elisa, again. Thank you, folks. We will not see you next Friday because of March meeting, but the one after will be back. So click like and subscribe, and see you soon.
Bye-bye.